Now, as we are ready with our Simulink block diagram, it is time for us to understand whether it is working fine or not, or whatever we have designed is fine or not. To do that, to understand the output of these results, we need to add the scope in this. That is, the scope will be like graph of your variables with respect to time. So we'll type scope over here, and then after scope we have this one. So this scope we can directly use from this place over here. Now this is for, we are printing phi theta inside, that is Euler's angles in radian. So we can see how the Euler's angles moves or behaves. So here we can type the Euler's angles. Now one other parameter we can check is this xyz, that is the position of a vehicle as the Euler's angles changes and as the time varies. So we'll copy and paste this. Now we have the same thing and we are connecting with this. See, keep in mind that after the integration it is showing xyz position, not before that. So connect accordingly. That means if you want to print xyz, then in the xy wire only, and if you want to print x dot y dot z dot, then you can connect over here. Now we'll change this as well here. This is basically xyz position with respect to earth. So position I am typing here. So first open this by double clicking on the scope. Now we have the scope and time is around 10 seconds, which is shown over here, this 10 second. First we are, as we are starting, so we are keeping the time small. So let's see how system behaves when, okay, and keep in mind, if you have not run this initial condition file, first you run the initial condition file, which is like flying at 100 meter altitude and with the forward velocity 10 meter per second. Rest of the parameters are 0. Okay, so running the simulation, only you need to click this green button over here, and now simulation starts. So it will take a while and it will take some time to complete, that is around 10 seconds depending on your steps. And as you can see here, the results are coming. Now these are the Euler's angles. As you can see, as this system is moving, the Euler's angle is changing quite a large. Now about the position, as we can see here, the position is like this yellow line. So let me add the legends over here. This yellow first one is for the x position, and then the second one, the blue line, is for the y position, and the third one is the z location or z position. So basically x, y and z. So z is basically our altitude, negative sign because the downward is positive and upward is negative. So in short, as you can see here, the position, as the pitching angle here, as the pitching angle increases, the altitude of the airship increases, but it increases slightly, not more than uh, like not a random number or not so very non-linear thing. The equations are non-linear and results are coming smooth. That means our design is quite good and perfect. Now we need to check for the longer period of time whether the system is stable or not for the longer period of time. So let us change the simulation time from here, and the simulation time we can take around say 50 seconds if we take, and after the 50 seconds see how Euler's angle behaves and other angles behaves, or in short the airship behaves. So this is what it is. As you can see in the left hand side, this Euler's angle is completely increasing over the time, and that angle is pitching angle, as you can see here. The third middle one is pitching angle. So roll, pitch and yaw, this is the order. So blue one is for pitch. So pitch is increasing over the time, and the altitude is also increasing over the time. So this is not so good. We need to change the or modify the location of the center of gravity, and which is here in this airship nonlinear dynamic function. Here we have defined these variables. So I think minus 0.1 is not working fine, so let's check with minus 0.5 first, and if it is not working well, then I think we need to modify to some other number. So we'll run with this. After changing, we'll run this and see how system is behaving. Right now it is looking smooth, but still, as you can see, the altitude is increasing. That means the pitching angle also increasing. Not so not so good. And one more thing, as we have increased from minus 0.1 to minus 0.5, the amplitude is increasing over the time. That means the in the pitch the system is dynamically unstable. So we need to change the location once again. So let us check with the positive number. Let's go with zero point 0.2 and see how system behaves now. So with zero point 0.2, after changing the zero point 0.2, we are checking the response, and the response is basically still the pitching angle is increasing, but it's more dynamically stable than compared to the previous one. But still the amplitude is increasing, is still showing the dynamically unstable system. But from the previous data, it is much better. So we'll change more, and accordingly, once we will be, I think after certain iterations or certain checking, we'll be able to get the perfect results or perfect number, which is very much desired for our system. So ultimately, if you see, we are finally getting the smooth results, but it is dynamically unstable in pitch, which we can recover after certain iterations. So we can say that our simulation and all the functions are properly defined and things are working well. Only few parameters we need to recheck, which is some of them are like k1, k2 and k dash, and then the location of center of gravity with respect to the center of buoyancy.